So I don't know. Okay. Yes. Okay. So I'm going to start this talk with just talking about the science of measurement, which is called metrology, and historically has heavily relied on atoms and optical measurements. And what we see up here on the screen is basically a lot of units for mass, for distance, for length, and then for time. And what these units are, they are basically the International System of Units, or SI units, which are base units from which basically all other units from which we can do any measurements can be derived. And the idea of why units are needed is because that's how we communicate and convey measurements that we do in our daily lives, and also when we're doing science. And the idea is that if you want to do a good job with measurements, you're able to determine these units to as precise a degree as possible in defining a physical quantity. And here, I've used the words both precision and accuracy, and I think it's useful to differentiate between the two. So here's a question for all of you. Feel free to just shout out the answer. So I've illustrated here multiple scenarios of what happens, for example, when you're playing darts and you're trying to have your darts hit the target, and different scenarios. So in what scenario do I have a situation where I may be accurate, but not very precise? B, thank you. And then what about the scenario where I'm just like completely precise, but then not accurate? I'm just off the bar. Yep, go ahead. C, right? And then of course, the scenario that you want to be in is one where you have the best of both worlds, where you're both accurate and precise. And we'll start with the definition of the second, which is a great example of what quantum technologies and atoms in particular can provide that level of precision and accuracy. Okay, so how we typically tell time is we need an oscillator, something, for example, can be as simple as a pendulum, something that swings back and forth. And you need a good way to keep track of these oscillations, right? And then you count the number of oscillations within a certain window, and you get time. And here, the atom actually acts as an oscillator. And in particular, we're looking at the way that the electron, an electron in the atom oscillates. And for cesium-133, that oscillation is at about 9.19 gigahertz. It means that it oscillates 9.19 times 10 to the 9 times within a second. And then you couple that with a counter that keeps track of the number of oscillations or ticks. And then you define, after counting however many ticks up there, that you have a second, and that's basically a clock. And if you compare this kind of oscillator, the atomic oscillator, with, let's say, what mechanical systems can do, which is give you a few to maybe tens of hertz, or quartz crystal, which is something that gives you, tens of kilohertz. What you find is that the atoms will oscillate at a much higher frequency, and this higher number of frequency gives you higher occurrences of these ticks within a given period, and that's what allows you to achieve this level of precision. And then if you couple, yeah, go ahead. Yeah, so I don't have it in this graph, but then if you think about if you have an electron in an atom, and it is bound due to various forces, right, to the atom itself, so it's not just escaping out of the atom. But if you give that atom some energy, it will actually change its energy in a quantized way. And if you have a way of basically changing that energy back and forth, let's say you excite the atom, you de-excite the atom, and keep going back and forth, that motion corresponds to, if you think about the electron not being as just a particle, right? It also has wave-like properties. So then the electron density distribution changes back and forth from one energy to another. and going back and forth, that's what's oscillating. And actually, that's a great question that leads into the next part of what I was going to show you, which is, so you can see that precision comes from like this high frequency. And then the accuracy comes from the fact that you can do this experiment, you can do this measurement in a very well-controlled environment. And this is a picture of the fountain clock, the cesium fountain clock at NIST, which is currently how we define the second. And you have all these instruments that are basically a lot of optical and electronic instruments and RF instruments that are used to do this excitation and de-excitation that causes the oscillation of the electron. And on top of that, you have a lot of controls, like what you see in that column up there is basically magnetic shield. And so what that ensures is that every measurement that you do, every atom that you prepare that participates in this experiment is going to behave identically. And that's what gives you that accuracy. Okay, so the way that we define a second is basically based on this, what is called hyperfine, and it's basically one type of energy transitions within the cesium atom. And let's actually move on to another type of measurement. So what I've shown here on the upper left are these platinum iridium meter bars, which is how we used to define a meter, the length of those bars. And of course, that means that you have to keep these bars in pristine conditions and then periodically measure them. So since the advent of stable lasers, this is back in sort of the 1970s, we can now then use another method of determining the meter, which is to measure the speed of light in vacuum. So you put the stable laser in a vacuum, and you have speed of light. You can measure distance, and you can also have a very precise measurement of time. And between those two, you can basically determine the speed of light. And then that's basically how you can now define the meter. It's just with the propagation of a stable laser inside vacuum. So yeah, it's the length of the path traveled by light in vacuum and 1 over the speed of official definition of the speed of light. Okay, so next we talk about basically the definition of mass, which is for the SI unit, that's the kilogram. And again, like before advanced technologies that allows us to have other ways of determining time and distance, the way that we define a kilogram is with these ultra pure, beautiful looking objects that are housed in vacuum. That basically weigh exactly a kilogram, right? So an example of these like ultra pure silicon spheres, now part of the Avogadro's project. And then there are these also platinum iridium kilogram masses. But that's, again, not the best way to define a kilogram. So then right now, the way that we do that is through measurement of the Planck's constant. And what you see in this picture up here is something called a Kibble balance, which balances electromotive force with mechanical force. And then that measurement basically gives you Planck's constant, which in turn gives you the kilogram. Okay, so this is just a quick overview of like how units are defined and how constants, fundamental constants in physics are defined, and also maybe small ways, right, that quantum technology is already contributing to that. And this is kind of a summary of all of that. Basically, once we have the definition of a second, once we have a definition of a which helps us define also the meter and the kilogram through definitions and and by fixing the speed of light and Planck's constant, you pretty much can derive everything else. And so what you see up here includes temperature, so this unit for Kelvin, ampere in measurements of electric charge, and mole is like kind of separate with the Avogadro's number. but basically all the other units can come from just the definition of the second. And as to why I started the talk with this and why this is all important, so obviously when you're communicating a physical, like the scale, right, and the property of a physical quantity, knowing what unit you use is important. But then also, if you're in the if you're in the business of just doing measurements and doing in particular, actually any type of measurements in the sciences, what's important is that if you fix the values of these constants, you have a great way. And if you communicate using the same units, you have a great way of comparing experiments, even if they are very different in physical nature. And that's actually a key part of like fundamental tests of physics, is basically to test these physics in different environments, using different methodology, and having fixed constants and fixed set of units basically would allow you to really compare these results. Okay, so before we dive into what are examples of quantum sensors, I want to give a few more examples, and one is that of navigation. So currently, the way that we go from point A to point B, if you don't know where you are, you basically whip out your phone. You use basically GPS on your phone to help you navigate through your favorite app of choice, right? And so the GPS signal actually comes from a constellation of satellites, and there are actually 24 of them, plus a few spares. And these satellites are distributed in kind of 6 orbitals with 4 satellites in each plane around the Earth. And the properties of these orbits basically ensure that at any given time and at any given location on Earth, you're actually covered. So for example, the orbital period of these GPS satellites of having 12 hours means that as a fixed observer on Earth, you are going to see the same satellite at almost the same place in your view twice a day. And the fact that you have multiple satellites on each orbital plane means that at any location on Earth, assuming that you are not covered, you will have 4 visible satellites at any given time. And GPS has on board, each GPS satellite has on board an atomic technology. That atomic clock that I was telling you about, that was based on cesium-133, you can make a similar atomic clock using rubidium vapor. And that's what actually can be found on a GPS satellite. There are multiple atomic clocks, which look something like this. So this is actually old technology, right? Because these satellites were launched many, many decades ago, right? And these clocks are still running. These are what is helping us be able to tell where we are and what time it is. And so these are called the RAVS clock, so that the R stands for rubidium. I think atomic frequency standard, probably that's the acronym. And inside you have rubidium vapor, and you have a lamp, and and then you also have RF oscillators. That combination basically gives you a very precise and accurate time that doesn't drift a lot over long periods of time. And so in terms of why this is useful, so let's see how we actually currently tell time. Tell our location using GPS. So we have 3 GPS. Let's start with the concept of triangulation, which I think you've probably all heard of, right? So if you have an observer on Earth, you're trying to figure out where you are. So then you see 3 GPS satellites, and each of them will broadcast you basically their location, their position, and then you can figure out the distance from the receiver based on if every time you get a position broadcast from this receiver, you also get a timestamp associated with it. Then the arrival time that the signal gets to the receiver will basically tell you what the overall distance is, right? And so then you have 3 measurements. Okay, then if you look at the overlap between these in a triangulation, then you basically get where you are in terms of your receiver location. Okay, so I mentioned that the distance being a crucial part, right, of this measurement. So you can imagine that if you have a small timing error, that's going to lead to a position error, right? So in this triangulation, what you're doing is you're drawing three circles based on the distance, right, and the position of the satellite, and where these three circles intersect is where you have where your location is. And so then any errors in this positioning will lead to an inaccuracy in the way that you determine your position. So if you assume that your atomic clock is drifting around 10 to the minus 14 seconds in a day, and 10 to the minus 14, and this is a fractional uncertainty, and that translates to about a nanosecond of drift time in a day. What that means is that your position uncertainty becomes sort of a fraction of a meter, which is roughly how we experience GPS, is that it's accurate, but then accurate to, let's say, within a meter. And one one small caveat to this is that, sure, you have very accurate atomic time from the GPS satellites, but we know that on our phones, we don't carry with us atomic clock, right? And so you don't only have the timing error of your atomic clocks on the satellites. You have worse timing errors if we're just using our phone. So does anyone have a suggestion of what we can do? So I use the word triangulation, but actually what is happening when we're using GPS to navigate is that we use 4 satellites. And the reason is that we have no way of getting very precise time on our phones, or unless you have your carry-on atomic clock with you. So we basically use 4 GPS signals in order to get the timing right. And then that basically allows you to find that perfect intersection and allows us to accurately determine where we are. Okay, so any questions so far? So we've just mostly covered kind of applications of of quantum technologies for sensing. Now we're going to dive into the actual technology itself. All right, so what is quantum sensing? So quantum sensing encompasses a lot of possible technologies, but then we're going to start with just the simple concept of the use of an object with quantum properties in order to measure a physical quantity. So it could be distance, it could be time, it could be different forces, electromagnetic fields, or inertial forces. And we need a physical system. So I've already mentioned atoms. So let's just assume, okay, we have atoms. We actually are enclosing this atom in some kind of vessel. And inside this vessel, we can then treat each atom as an isolated quantum system. It's not always the case, but we can control the environment such that that is the case, so you don't have to worry about interactions between the atoms. So then within each atoms, we've already discussed the concept that, okay, you have bound electrons, but these electrons, even though they're bound, you can actually put in energy and you can excite these electrons and then have them be de-excited through various processes. And so then the energies that can be occupied by these electrons have to be quantized. And that's one of the fundamental properties of quantum mechanics. The way that these electrons interact with the nucleus will lead to basically quantized energy solutions. And so if you have a way of measuring these energies, and you can measure it in the form of, you typically don't measure just energy, right, of the electron. What you measure is changes in that energy. And you do that through basically changes in the oscillation frequency. And you can measure that through the light that may be given off by the decay of that electron from a higher energy level to a lower energy level. But you have a way of probing these discrete energies, or rather the differences in these discrete energies. And you're measuring that in terms of the frequency or energy or wavelength, whatever. And you have physics models that basically tie these frequency transitions to the interaction between the atom and the environment. So basically, any changes to this frequency or energy can be mapped to changes in the external magnetic field, to maybe the motion that's being experienced by the atom, or to temperature. And I have this equation up there, which is okay. So what you're measuring, and then the thing that is affecting is change. And when we're talking about developing a sensor, the concept of sensitivity is basically the smallest detectable change you can have. Let's say in the change in magnetic field that leads to your measured frequency change still being detectable and kind of deterministic, right? So you can imagine that any measurements will have some noise. Any measurement will be subject to systematic errors, right, in your instruments. And that systematic error is basically another source of error. But then when we're describing sensitivity, we're really describing the impact of like measurement noise, and also fundamental limits of the physical system on the smallest detectable change. Okay, so that's basically so this is the simplest definition of what quantum sensing is. Okay, you can actually add some complexity now. Okay, so there's also other quantum effects that come into play, right? So there's this concept of coherence, and probably easiest to explain the concept of coherence by just talking about waves. Like, what am I talking about in terms of coherence is you basically maintain this. So let's say you have this waveform that this wave packet that propagates through space and time. You basically maintain this envelope, even if it evolves in the medium over time and over long distances. And that concept of coherence can come in the form of, let's say, when you're dealing with a single atom, you can treat it as a particle. You can also treat it as a wave, right? How long can you still assume that it maintains its initial wave-like property is one way to sort of think about this concept of coherence. What is another kind of weird quantum phenomena that you hear a lot about? Entanglement. So then, thank you. That's the next one that I want to talk about that I won't go too deeply into today, but then I do want to mention it for completion is that sometimes quantum sensors, once you've exhausted all the tricks you can play in terms of improving the noise of your measurements so that you are really pushing the limits of this sensitivity, and you need more knobs, then you actually can bring in concepts of entanglement and doing measurements on, let's say, multiple quantum systems that are themselves entangled in order to further push your sensitivity. Okay, so now let's actually talk about physical systems, right? So I talked about atoms as one of them, and we'll spend the next sort of 20 minutes or so on talking about sensors that can be built using atoms. And what you're seeing here in this presentation is, in this lower picture is a vacuum cell. Like, so this square thing is basically a vacuum cell. Inside has rubidium atoms, and we have trapped basically two cold atomic clouds on these opposite ends, and they're very cold, on the order of, well, it depends on who you talk to, I guess. They're relatively cold, few tens of microkelvin, and they each contain about basically millions of atoms. And you can also get analogs of these trapped atoms, right, in the solid state. And that actually comes in the form of these color centers. So what I'm showing here is basically a bunch of diamond crystals with different colors. And that actually comes from defects, meaning either a missing carbon atom or substitutional atoms inside the diamond crystal. And it turns out that these can be considered to be artificial atoms. because they behave very much like atoms that are being trapped, let's say in a vacuum, and have they can now have discrete electronic transitions that are useful for sensing. And I should also mention that I believe tomorrow you'll hear about some other examples of artificial atoms in the solid state, and particularly in like silicon and germanium materials. And this is basically the same concept. Okay, so what we need in order to do these quantum sensing measurements is we need discrete electronic transitions, which you can get in atoms and also these artificial atoms. And what I'm showing here on the right are basically one example of these electronic transitions, right? And what you see are basically optical transitions, and these are derived from what I call fine interactions. And in the case of rubidium and cesium, these are in the near infrared. And by that, I mean kind of in the 700 nanometer all the way to like 852 nanometer in wavelength. And you can also then utilize interaction between the nucleus and the electron spin. And that gives you hyperfine interactions. And then so you have these further splitting in your electronic structure that basically gives you in the ground mode state, meaning that the state that the outermost valence electrons like to occupy, like to sit. You have this ground state hyperfine splitting. In this case, I'm showing here for rubidium-87 is 6.8 gigahertz. For cesium, we just talked about that being used as our timing standard. That's about 9.2 gigahertz. But it's really this ground state hyperfine transition that is responsible for a lot of the early atomic clocks. And then in the excited state, you also have further splitting, but we won't talk about it right now. Okay, so first thing that I'm going to do is, okay, what happens if I put this atom in a magnetic field? And what you get is basically you start seeing splitting and further splitting in your hyperfine structure. And it looks kind of like that. So if we think of this axis as energy, right? And then this axis, let's say, as strength of magnetic field, you start seeing that you have splitting in the structure that gets worse and worse, right? Not worse and worse, but that gets bigger and bigger as you increase the magnetic field. And you can actually predict that with physics model is something called the Zeeman effect in the lower field limit. And so then what we're showing here is already one way to measure magnetic field, right? If you're doing spectroscopy on this atom, and you're just keeping track of how many split lines I have and how far apart are these split lines in frequency, then I can convert that to an actual magnetic field that I'm sensing, assuming that I know the scaling factor, which thankfully for an atom like rubidium is actually fairly well predicted. Let me try to get rid of this little hotspots. Okay. So so far we've talked about how we can measure magnetic field. Let's talk about why we're using atoms in the first place. So going back to this kind of word formula, right? Like so. Why atoms and atom-like systems are great is because they're very sensitive to these external disturbances that basically changes your energy transition. They can have small length scales, right? Each individual atom is on the order of an angstrom. And one of the nice things about working with atoms is that if you prepare many atoms the same way, as long as they're in the same species, they will behave the same. And in a way, it's kind of an ideal measurement standard in that individual atoms have properties that don't degrade. If you, let's say, send in resonant light and you just look at absorption of a single atom, you'll see a tiny absorption dip. And then if you do the same thing on a bunch of atoms, you get a much bigger signal. But then there's an element of indistinguishability, which means that your measurement noise only improves and doesn't get worse when you do these ensemble measurements. And then the last piece is that you can leverage, coherence and entanglement to further boost your sensitivity. And so just to give you some kind of benchmark numbers in terms of the power of these atomic systems. So you can do these spectroscopy in a sense, right? You're just measuring energy and frequency transitions to determine, we've talked about timekeeping, where right now the best uncertainty at a second is now down to 10 to the minus 17 seconds. And that this type of measurements utilizes not microwave transitions like we talked about, but rather optical transitions. And again, the same concept is that if you are thinking of the measurement of time as just counting oscillations, the closer those oscillations take place, right, the more accurate and precise your clock is going to be. And that's the idea behind using optical transitions. Their frequency is on the order of hundreds of terahertz as opposed to a few gigahertz. And you can measure magnetic fields down to basically an attotesla. So I leave it all to you to think about what you could do with such a magnetometer that can give you an attotesla, right? That's a number that's a little mind-boggling because most of the time, like even in a fairly well-shielded environment, you have your background magnetic field way overwhelms that, but atoms can give that to you. And then you can also measure inertial forces, which going back to the application of using GPS for navigation, you can imagine that there are scenarios, and we've all experienced that you have very poor GPS signal, right? So there, do you want to rely on your instruments, which may not be accurate to navigate? And most of the time, that's maybe good enough, but in certain scenarios, you may actually want something better. And atoms can actually give that to you. And in particular, an accelerometer that's made using atoms can have uncertainty in a second way lower than 10 to the minus 9 G or 1 energy. So the measurements that we have to do to really take advantage of all of that is typically actually involves optical measurements. And that's because the way that we measure atoms typically uses atom-light interaction. So the way that works is, let's talk about the processes of absorption and emission. I've already talked about, okay, you have these discrete energy levels, and then you can send in resonant light. It will get absorbed. So what that corresponds to is the electron being excited from ground state to excited state. And then after that, you have multiple ways to go, but I'm going to focus on two. One is the process of spontaneous emission, where you just get a photon being emitted in a random direction. And then that tells you basically whether you have excited that electron to the excited state, and then also whether it has decayed back to the ground state. So that, in a way, tells you the existence of that atom, and it will tell you, in certain scenarios, basically the exact state that the atom ends up in. And then the other process is known as stimulated emission. So the idea is that you're sending in coherently, let's say, streams of photons that excite these electrons from ground to excited state. Then once it is sitting up in the excited state, before it has a chance to spontaneously decay, it actually is coherently driven back to the ground state. And so what you get out at the end is basically two identical photons, and it's known as a process of stimulated emission. And this is a useful technique when you're trying to coherently drive the electron to go from one state to another, back and forth, back and forth. And that process that I described with regards to the atomic oscillator is based on this concept. You're not really relying on any spontaneous processes to have the excited atom decay back to the ground state. You're actually coherently driving it. Okay, so the way that you do this in the lab, and I know tomorrow you're visiting Professor Mark Saffman's lab, which has a lot of these setups and that look way more complicated and sophisticated than the above. But then what you see up here is basically a couple of these semiconductor lasers. So basically they are distributed broad reflector lasers that emit it at 780 to 795 nanometers. And we direct that to a rubidium vapor cell that you see up there. And this is really just at the edge of what you see with your naked eye. You see it kind of reddish in color, but really the right way to image these beams for safety is to wear a proper laser goggles and then just image that with a viewer card, which has these materials that basically fluoresces when the beam hits it. And so what we do is, when these lasers come and we set them up, they're not really referenced to any specific wavelengths, right? You can change the current, change the temperature to slightly shift the frequency. But then what we need to do is then have these lasers interact with the atoms in order to basically lock them to a specific frequency. And you do that through spectroscopy. But in the bottom is basically an example of that. You're scanning the laser frequency, and I will only look at the yellow trace. So basically, we're looking at a time series of the detector signal after the light has interacted with the vapor cell. And we basically see big absorption dips that have to do with the excitation from one hyperfine ground state to an excited state. We also see two dips due to the different species in rubidium. And then we are able to also resolve hyperfine structures. And then we lock to any one of these transitions. And that basically allows us to have an atomic or an atom reference laser. Okay, so that's only really the first step of doing any of these optical measurements. You know where your laser frequency is sitting. You have high degree of confidence of the frequency. Then in terms of how it interacts with the atoms, there are many approaches, but typically a common technique used to ensure that when you're starting a quantum measurements, what you want is for all the atoms to basically sit in the same state at the beginning, right? Because otherwise, if you have no idea what your starting point is, how do you really tell what your ending point is? And the way that we do that is with a technique called optical pumping. And you can just think of the atoms as behaving individually like spins, right? We have the concept of we're really using light to interact with the electronic degrees of freedom, but then we know that each electron also has the property of spin. And the way that we can have the light interact resonantly and deterministically with these atoms is to basically apply kind of near resonant light. And that light has to be of the right polarization. And when that happens, you're practically aligning the electron spins in the same direction. And what's happening in terms of the energy is that you're going through this process of absorption and spontaneous emission over and over again. And because of the specific polarization of that light, you end up populating in a particular ground state. And then that ground state corresponds to all the atoms then being aligned at the beginning of the measurement. And you also know what state you're starting with. So after that, you're ready to basically do your quantum measurement. And what you then do next is let's bring in an external field. And one of the easiest things you can generate in the lab is maybe a magnetic field, either with kind of a bar magnet, or you can build a Helmholtz coil like I've done up there, and then put a vapor cell in the middle. And so you apply a magnetic field. So now going back to this analogy with kind of spinning tops, you have an overall atomic spin polarization. You have an external magnetic field. What happens if you have a spinning top that spins and you kind of apply some mechanical force to tip it? What kind of motion do you expect to see? Yeah, go ahead. Yeah, gyroscopic motion, which are some kind of precession, right? So you have this precession motion, which is, you can think of the same thing as happening to the atoms. If you then apply a magnetic field, then you have this precession motion that you want to measure. And that precession frequency, what is that determined by, you think? So if you have a spinning top, is it going to precess the same way no matter how hard I push it? Most likely not, right? So here, that precession frequency that is experienced by the atomic spins basically is going to change depending on the strength of the field. And so then if you're able to measure this precession frequency, then you have a way of then transducing from that magnetic field to a measurable signal. And what that measurable signal is, turns out, is still an optical signal. So what we do is we apply a probe light. Again, a probe light could be relatively resonant, and it comes with a well-determined polarization to start. And this probe light interact with the atoms, and you can think of that interaction as imprinting the polarization of the atoms onto the polarization of the light. So at the end of that, what we see is a change in the optical polarization of the atom. And so what we've done is a transducer now from the magnetic signal to an optical signal. And this whole measurement basically just involves first optical pumping, then a probe with a well-known polarization at the beginning to basically detect the change in the polarization of the atoms through an optical polarization change. And this actually allows us to really sensitively measure magnetic fields, and then maybe skipping ahead to this scale that I like to show from a thesis back in 2008 of like the scale of magnetic fields that are that exist and that are measurable, right? Earth field is on the order of microtesla, and if we're talking about what the atoms can do, which is below a femtotesla, and so femtotesla is typically 10 to the minus 15. And that basically can allow you to measure various biological signals, right? So including small changes in terms of the firing of the neurons in the human brain, motion across the blood-brain barrier, and then also applications in detecting sort of human heart, for example, a fetal heartbeat. And so this leads me to some applications of kind of the simplest type of quantum sensors that you can build with just a vapor cell and a laser and detector. Basically, you can imagine it could be very useful to take out of the lab and measure various changes and geomagnetic signals, right, as you go across the terrain. So maybe, I don't know how many of you are from where you are from, but then anyone recognize this map up there? Which state it is? It's Wisconsin. So what it is basically is a USGS map of the magnetic anomalies. And what that comes from is basically buried under us, right? All these crustal features that really don't change on geological timescale. So they actually are very stable over time. And these crustal features have heavy elements, right, that lead to magnetic field changes. And you can actually see these changes across, let's say, it's the state of Wisconsin, which is actually relatively flat. But even then, you have about 1,100 nanotesla scale variation, something that would potentially be easily captured by an atomic magnetometer. And this is sort of one potential application of these magnetic sensors, is the ability to basically couple magnetic measurements with, let's say, a map that you trust in order to sort of figure out where you are in the case where, for example, you don't have GPS. Yeah. 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 That I don't know, like that, because it is true that like birds basically have like magnetometers in the brain. Yeah, I think I have to look up how precise that magnetometer. I think the effect for birds is not necessarily they're not necessarily looking for specific features right from the crust, but rather it's more like a north finding feature where they can tell. Another application, right, is for magnetometers would be to figure out where north is, where true north is, because you can measure Earth field. But that's a great question. I think it's north finding and kind of gyrocompassing. Okay, so then that leads me to another sort of class of applications, which is detection of biomagnetic signals. I always like to show that picture up there because it's of Professor Thad Walker in the physics department, who is one of the world's experts in developing these atomic sensors. And what Professor Walker is testing here is a magnetic field sensor for potentially testing fetal heart rate. So this is known as the application of magnetocardiography. So what you see up here is also like a bunch of optical fibers, right, developing optical signals into the sensor head. And then these two figures basically show what potentially a system for measuring for doing magnetoencephalography, which is basically mapping blood-brain barrier in your head, looks like using atomic magnetometers. Currently, what is being used are squid systems, which tend to be a lot more bulky and harder to manage. Okay, so I've talked about so far basically using hot atoms. And then I've shown a couple of slides ago also some pictures of cold atoms, and maybe I want to motivate a little bit why sometimes we might want to cool down atoms. And so let's think about first, when you have atoms in a vessel, what the atoms are doing. So we expect the atoms to not just be stationary, right? It's going to move around, and it moves around according to basically the kind of the thermal energy, which then amounts to kind of the average temperature, right, of these atoms. And so if you have atoms at room temperature, you can then think, okay, starting from time zero, if I just let it go for some time, where are my atoms going to end up? Basically, the atoms are going to be moving at about 300 meters per second, which means that within a millisecond, you would have like, lost all your atoms to like maybe 30 centimeters away. You don't typically have vacuum chambers that are that big. And whereas if you think about the atoms as starting very cold, let's say just a few microkelvin, then the speed of these atoms is about 0.2 meters per second, 2 centimeters per second. And in a millisecond, the diameter only expands to about 20 microns. So that likely is still within the size of your laser beam, right? And that the atoms are still within observable range after this movement. And so then basically this hopefully gives you a little bit of motivation on why sometimes you may want to cool down atoms. And you really see that motivation probably when you hear Professor Safran speak, right, about the whole idea of neutral atom quantum computing is to basically cool and trap these atoms so that they are in a location that you can readily address with lasers. And even for sensing, even though sometimes you may not need to cool down atoms, once you cool down atoms, you have the benefit of having this really nice spatial resolution. It's really well defined in space, and then the atoms also will remain coherent for a much longer time because it doesn't just get spread out very quickly. And so I'm going to skip over like the mechanics of cooling and just say that, okay, cooling is going to be based on the interaction again between light and individual transitions in atoms, and we're using that process of absorption and then of spontaneous emission again, and do it over and over again. It has to be of a specific transition that's kind of special in that doing this cycling over and over again is going to lead to atoms dissipating energy, and it's going to have to rely on the atoms also seeing redshifted light, meaning light that's not perfectly resonant, but it's slightly redshifted. And that has to do with the Doppler effect, that basically you want atoms traveling in one direction to basically see this redshifted photon so that when it absorbs, it actually gets a recoil in the opposite direction that counters its thermal motion. So let's say that, okay, we're doing all of that. We have light coming in different directions, and typically you need kind of 3 different directions and 3 sets of counter-propagating laser beams to basically cool down these atoms. On top of that, you add a magnetic field, and this is a magnetic field gradient that basically pushes all the atoms into the center of the trap. And the picture that I show up here is in our lab of a vapor cell. So this glass cell has already rubidium atoms in it, and then it's flanked by these anti-Helmholtz coils that generates a quadrupole field. So what that quadrupole field looks like is that it has a field zero in the middle, and then along this z direction, this vertical direction, you have basically a few gradients that get stronger as you approach the coils. And then if you do all that, you get basically a trap in the middle of this chamber, and then it looks something like this. And here you see this glow. This glow actually comes from fluorescence of this rubidium atom, right? And I have a picture that basically shows how it changes if you, let's say, turn off the magnetic field. So you basically have these atoms that scatter everywhere. And then I don't remember if I have a picture, I have a video. I don't have a video, but if you then bring in a little bar magnet, you can then steer this magneto-optical trap around. So this is what is called magneto-optical trap. So for context, this is a very common technique that basically cools and trap atoms down to, let's say, maybe tens of microkelvin. In tomorrow's talk with Professor Sepman, you'll likely hear about these arrays of neutral atom qubits, right? Those actually typically start off with this magneto-optical trap, and then on top of that, you bring in optical tweezers, which are, you can just think of that individual laser beams that basically create this optical force that basically confine the atoms in space. Okay, so now moving on. Okay, so we've talked about how we generate these systems and some of the applications, which include code atoms, using code atoms for timekeeping, and then the ability to be able to do maybe tests of fundamental physics and improve our measurements in regards to geodesy, which is kind of like the shape of the Earth. And to do all that, you need really good timing, which is given to you by the atomic clock. And then you also need to bring in another technique to really carefully and sensitively measure inertial forces. And here I wanted to bring the concept of treating the atoms as each individual atoms as a wave packet, which I alluded to before. But let's say that you have an atom, you know how to compass, so it starts off in the right state, right? Let's say you have a way, because you're confining these atoms with lasers, maybe accelerating these atoms by just changing the frequency of the laser so that you're using a Doppler effect to kind of push the atoms in one direction. So you're giving it an initial momentum kick. So it starts with some momentum. So atom is behaving as both this particle and a wave. So you can think of it as also kind of equivalent to if you have a light beam and a light wave, and you're just sending that light wave, let's say, down a path. And now let's say that we have a beam splitter, like what a beam splitter does to an atom is that to a light wave, right? It actually splits the light wave into two possible paths. A beam splitter for an atom wave will do the same thing. So here on this plot, I have both of these are in spatial dimensions. So I'm initially sending this atom along the y direction, and then I'm adding a beam splitter that allows you to basically split apart the wave packet kind of in the y direction. Oh, sorry, in the z direction. So here I open up my interferometer. One arm, actually, I'm not adding a momentum change. And then the other arm, I'm adding this momentum kick, and that's why you have this splitter. And then I'm going to do what is equivalent of a mirror to this the propagation of these two paths. And that actually bends the path trajectory of these two possible paths back towards each other. And then in the end, I add another beam splitter that's like a mixer. So what I'm drawing here is perfectly analogous to optics of what is called a Mach-Zehnder interferometer, right? Where you initially split the light wave, you deflect them back towards each other, and finally recombine them. And what happens at the end of an interferometer? What do you get? fringes, right? We expect to see light fringes if it is with light, and that corresponds to having dark and bright bright spots. If you're looking at things either spatially or if you have a detector and just detecting what you're observing as a function of time. You can do the same thing here with atoms. You're basically measuring then the phase changes of the interference associated with the atom, which actually can be done with just a fluorescence measurement of just one of the atomic states. And so I'm going to skip over kind of details of that. Happy to talk more about that later if you have questions. But the key is, okay, we're just using the atom as a matter wave. And we have a way now of measuring the interference, which ends up being a function of the inertial force experienced by the atom. And that's my very simple explanation of how that happens. So in the original dark lines that I drew, right, is the case where, let's say the atom is in space, is experiencing no force. So if I throw it across the room or across my chamber along Y and just apply these atom optics like beam splitter, mirrors, mixer, whatever, it's going to trace out that kind of parallelogram where in the end you just get an interference signal where that change in interference is going to give you the path length difference between the upper and lower arm. If now I'm shaking my chamber, I'm adding, let's say, some acceleration, then what I'm going to see is one trajectory is going to look longer. And that's going to give you a phase change. And it's not just acceleration, right? There's also rotation because, anything that basically leads to one path being longer than the other is going to lead to a phase change. And so then you can measure this phase difference and map that to your acceleration and rotation signal. And it's going to, you don't have to dive deeply into the formula here, but just know that, okay, you can actually map that out. And this turns out to be a really good technology in measuring inertial forces. So here are just some examples of some of the field deployable atomic sensors. This up there is basically a gyroscope. Actually, it's a gyrostabilized quantum gravimeter that's being used to on the port of a ship to basically measure gravity changes during the ship's mission. And this up here is basically an example from the Mueller group in Berkeley of mounting one of these gravimeters on a truck and going through the Berkeley Hills. And this is a little bit different. This basically is an example of an atomic clock that's been mounted on a rocket. Okay, so what you notice in all of this is that we're not necessarily talking about very big instruments here, very small instruments here, right? Like, so you have like these big packages, not necessarily very convenient form factors. So what I wanted to talk about to end sort of the part about atoms is that there's a lot of things that we can potentially do to make these atomic sensors smaller, and that's an active area of research. Couple of examples, and I actually brought some hardware to pass around. Okay, so I mentioned that we need to send in light, right, to cool atoms, and we actually need 3 beams sometimes, and they each have to be counter-propagating. Well, instead of sending in free space beams, maybe we can do all of that on a grating. And so I've shown a couple of examples here, including one here that we're starting to work on the lab. So what you see here is in the bottom is a grating chip, and what it does is that you have one light sending down, and you have basically diffraction from that grating that basically creates the other beams that are needed to basically cool the atoms. And I'll pass this around in a second, and be careful with this very weak laser pointer. Actually, Sarah, you know where this laser pointer is from? It's from one of our outreach activities. So what this has is basically it's a bunch of gratings that when you send in light in one direction, it'll give you diffraction into multiple orders, and I can bounce it here. So you can actually see these different orders. I don't know if you can see that easily here. So you can see these different orders that basically are acting to help cool your atoms. So that's one way that basically allows you to shrink down, a part of your optical table into just one chip. And I'll just pass it around here. This is a very low power laser pointer, but try to not maybe use your hand to shield it a little bit to not shoot light into each other's eyes. Sure, yeah, thank you. And then the other thing that I was going to pass around is I mentioned that we need to make these quadrupole field, and instead of using coils that you hand wind in lab, we can now print integrated circuits really easily and very cheaply. So then this here, right, is one of those integrated circuits that can be used to basically trap atoms on a chip. So you can imagine both of those things that I'm passing around in combination will then basically give you your magneto-optical trap. And this is one example of like a trap that's generated using these technologies. So I'll pass this one around here. This one is just a PCB board. Thank you. All right, so any questions so far? I feel like I'm talking maybe a little bit slowly. I've a lot more slides, but I don't have to go through all of them. Any questions so far before I move on to my next topic will be talk about kind of analogs of these atoms in a solid state. All right, if not, then I'm going to keep going. So my segue into what I want to talk about next is, okay, we look at, I like this image that I took from a paper on various quantum magnetic field sensors. And I think the reason why I like it is it conveys the scale of both the sensors themselves, but in terms of what they can measure, right? You can measure kind of spatially separated signals on the kilometer scale. So basically you can measure Earth field. You can then also measure down to the atomic scale, like down to the level of an atom. But the sensor that you would select for each application is kind of different. We know that atomic sensors are very sensitive. They are also ultimately limited by the fact that you're going to need a vacuum vessel. You are going to have to figure out some way to shrink down your lasers, your electronics, right? Like with the stuff that I'm passing around. So for applications where you do need to get to the atomic scale variations in your features of interest, whether it be magnetic fields or temperature or whatnot, you actually need something even smaller. So how small can you prepare, let's say, an atomic sensor? Well, okay, so you do need a vapor cell, right? And that already gets you kind of stuck in terms of the actual physical size of your vessel to kind of millimeter scale. And then let's say that that's not a problem, like you just want to have some kind of spatial resolution. Then you can use optical traps, right, to make, for example, this is from Antoine Bourret's group in France, where they trap arrays of atoms using optical traps. There, you have a fundamental limit from the optics. Does anyone know what that limit is called in terms of how closely you can place these atoms each other, or maybe rather how tightly can you focus your beam? I've already said that word in reference to the grading that I'm passing around. What is that fundamental limit? Anyone remember? Does the concept of diffraction limit ring a bell a little bit, maybe? It comes from the wave property of light, right? You're using light waves to create these traps. And ultimately, there's a limit to how tightly you can focus that. And that's known as the diffraction limit. That's normally hundreds of nanometer. And that's actually limits your resolution in that way, your ability to place these trap atoms next to each other. So we have if you really need to get to that level of precision, you have some options there. And you can actually take from the field of solid state physics, where you have these crystalline materials. What are crystalline materials? They're periodic arrangement of atoms. And if you have means to deterministically pluck defects, pluck atoms from this crystal, you generate what is called a defect. And if you just remove an atom, that's just a vacancy. And then if you add an atom, where, so what I'm showing up here is basically carbon crystal, diamond crystal with periodic arrangement of carbon. If you then plug an atom and substitute it with another atom, that's called a substitutional defect. And turns out there's a big class of wide bandgap semiconductors, meaning semiconductors where the separation between the conduction and valence band of high enough energy that the materials tend to be optically transparent. And that's useful because if you're going to make optically active emitters inside the material, you don't want it to immediately get absorbed by the host matrix, right? You want the crystal to be good host to these defects. And it turns out that the behavior of these type of defects in crystal are very similar to those of atoms, and you can actually make quantum sensors that way too. And so I'm going to try to be now a little bit quick to leave time for questions so that you can also get to your lunch. But then I want to just talk about the use of diamond as this type of quantum material, where you can kind of make different, what we call now color centers, which are analogs of these trap atoms in the diamond crystal. And depending on the type of defects, whether you have nitrogen, a lot of nitrogen in the crystal, whether you have boron, hydrogen, or just like a bunch of vacancies, you get different colors. They don't all lead to great quantum applications, but certainly they lead to great looking jewelry, which is, of course, at least my entry point to, knowing that diamond can have defects is that it's just by the fact that we have like different color jewelries, right? And so it turns out that even clear diamonds, like for example, there's a nominally clear diamond ring, it still has color centers. If you put it under a UV light, you can actually see all these like different colors popping up. So let's maybe talk about quickly how we can do that, how we can make that in the lab. So none of the diamonds that I work with or any researchers in the field work with are natural diamonds. These are all made in lab-grown diamonds. And the way that you need is you need chemistry. You need typically fairly high temperature and sometimes high pressure. And so you can start off with diamond crystals that are either very pure, meaning that have very, very low level of nitrogen. And we're fixated on nitrogen because we're kind of surrounded by it, right? So if you don't do a good job trying to keep that level low, your sample is going to be filled with them. And you can also start with yellow diamond, which are diamonds that are grown, maybe not under very carefully controlled situations, or maybe even grown under a rich, nitrogen-rich environments that actually ends up having this yellow color. And I'll pass like examples of that along shortly. And so we then actually to perform ion irradiation, which means that we are going to take this nice lab-grown, not inexpensive diamond. We're going to damage it some more. We're going to send it out and just shoot, like, let's say, a nitrogen ion beam at it. And what that does is it knocks off carbon atoms. It lodges some nitrogen atoms inside the crystal. And then after that, the crystal is fairly damaged. So then we actually heat it up. Before I get there, I want to mention different ways of like doing this irradiation. So you can do it with an ion beam. You can do it with focused ion beam. You can also do it like whenever you have really energetic ions or like subatomic particles. Like, for example, this is UW-Madison has a nuclear reactor. This is basically the bottom of that nuclear reactor when it's operational. What the glow that you see is basically Cherenkov radiation. And so what you have are really energetic neutrons that are in the bottom of this reactor. So you can stick your diamond in there too. That will also irradiate your diamond. Afterwards, you heat it. You heat up your crystal and you kind of heal a lot of the defects that were generated. And then finally, you clean it up and then you're ready for your experiment. So what I want to show here, maybe I'll do that after this next slide, is basically one specific type of defects, which is the nitrogen vacancy center. That's a missing carbon atom next to a substitutional nitrogen. So vacancy is shown as white. The nitrogen is shown as blue, and then all the carbon atoms as purple. It's in this diamond crystal. You measure it with a fluorescence microscope, and that's because if you look at this energy level diagram, it looks very similar to the energy level diagram that I was showing earlier with rubidium, right? You have some kind of ground state, hyperfine ground state, excited state, that the separation between the ground and excited are in the optical domain instead of the near infrared. Here we have basically a red transition at 637 nanometers. And due to the fact that you're in a crystal, you have a lot of what is called phonon activities, which means that, and it's helpful in this case, it means that if you're sending in light, that doesn't quite match the 637 nanometers, you still have a way of exciting the electron in the boundary excited state, because phonon is helping you relax those electrons back to that excited state. So, so you can send in incident excitation. Typically, you use green, and then you get red photons out, but you can also use different colors. And what I have here that I'm going to pass around is basically two diamond man-made, lab-grown diamond crystals. The yellow one is similar to the one that you saw in the previous slide that have like a lot of nitrogen in it. It starts off having a lot of nitrogen. This darker one, it kind of looks reddish, is actually one that we did stick inside the nuclear reactor. And for a few hours, and then when it comes back out, we anneal it. So we confirm it's no longer hot, so it's perfectly safe to handle. But you see immediately the change in color, and that's from the generation of these type of color centers. And if you then send in, I didn't want to pass along a powerful green laser, so I brought kind of this UV light. You can actually see the red glowing. So I'm going to pass it around so you can take a look at the difference between these two crystals. And so the only thing to do with the UV light, don't put it on your hand. You'll feel a little bit of heat, but try to not do that. Okay, so let me then quickly get to the punchline of what you can do with it, because I think I'm running out of time and we're getting close to lunch. So some applications of this, it's okay, these are non-sensing applications. You can actually make really nice high power stable lasers because diamond has excellent heat thermal conductivity. It is host to all these color centers. Wouldn't it be nice if you can manage to basically drive these coherently and actually make new types of lasers? That's one application. These types of emitters are quantum emitters, right? What that means is that the light that they emit, if you're looking at a single emitter at a time, they have non-classical nature. They have non-classical statistics, meaning that they behave like single photon emitters that emit photon potentially in a deterministic way. And that's useful for quantum communication. And actually, one of the first examples of demonstrating long separations of qubits that displays the Bell inequality theorem is basically done using nitrogen vacancy centers with physically separated NV centers in different diamond samples across the TU Delft campus, separated by more than a kilometer. Okay, so now going back to sensing. So as promised, right, we can indeed run these as sensors. And the way we do that, we use a technique known as optically detected magnetic resonance. And I'm out of time to really explain what it is, but you can think of it as, again, using an optical measurement as a way to basically measure the spin state of the quantum system, which is not a concept that's foreign to this talk. And so basically we are using this MV center to measure the changes in magnetic fields that it experiences, and we do this optically detected magnetic resonance measurement. And that actually allows us to measure magnetic fields. The other thing that it allows us to do is actually potentially measure vectromagnetic field. And the reason is that as opposed to atoms that don't have any preferential directions, right, when it's isolated in a chamber, in a diamond crystal, these defects, right, have to be grown along one of the crystallographic axes of the diamond. And that actually gives you that vector magnetic field signature. Okay, so maybe let me keep going. I know you just heard a talk from Professor McDermott on superconducting qubits. So probably you've seen some version of these timing diagrams, which is like, sending in pulses to basically do coherent control of your qubit system. You basically can do the same thing with NVs, and that's all I'm going to say. Maybe I'll just kind of end with some applications, which is the advantage of these systems, which are inherently actually not as sensitive as atoms, is that you can really, the whole reason why we started talking about it is you can really get to the atomic level resolution. You can isolate a single defect, and that's atomic scale. You can put that very close to the surface and really have them trap them just by their creation one at a time, right? And that gives you excellent spatial resolution, and that allows you to maybe look at cellular processes. And that's actually on this slide, right? This slide shows basically if you put some of these NV centers in cells by using nanodiamonds, you can simultaneously measure changes in magnetic fields as well as their temperature and correlate that with their temperature, all using very similar measurements. Okay, so maybe since we're out of time, I will maybe skip this part, which is I worked with a rocket team at UW-Madison to basically launch one of these magnetometers into their sounding rockets. So these are systems that are pretty much almost ready to be field deployable. And then maybe just end there. Yeah, there, of course, as with the atoms, there are some challenges. And again, like both photonic engineering and doing surface chemistry actually helps a lot with making sure that you have bright, coherent color centers. And then maybe I'll just end here and hopefully open the floor up for like maybe 2 minutes of questions before you all have to head to lunch. But yeah, hopefully I give you a flavor of different types of quantum sensors, and look forward to your questions. Thank you, everyone. Yeah, excellent question. It depends on what you're trying to do. If you're really, if you really would like to spatially locate, let's say the magnetic signature of down to sort of the tens to hundreds of nanometers, then of course you want to isolate. Let me actually put up this slide, which I kind of skipped. The reason why you want to do this in a microscope is because you could spatially isolate these individual defects and make them in a way that they're separated enough that you measure them one at a time. But then, of course, if you just care about, let's say, using an entire diamond crystal that's filled, like in the sample I'm passing around, is like literally filled with these type of defects, then you benefit more from just measuring the entire crystal. And there you won't want to use a microscope, right? You want to use some other methods of excitation and collection. Mm-hmm. Yeah, so that's an excellent question. That's one that I skipped. Basically, the measurement, right, involves you do optical pumping with green, and then you collect fluorescence. And then while you're doing that, you're exciting this roughly 2.87 gigahertz. But as you pointed out, okay, as opposed to atoms, it is harder for two NVs to be exactly the same. So there's always going to be a little bit of variation. And that's because you're just in this crystalline environment. And then so typically in experiment, what we do is we scan this frequency to isolate this zero field splitting, as you say. And sometimes nominally zero field splitting is not perfectly zero field because you have strain in the crystal. So you still see a splitting. And then after that, you apply magnetic field. And actually, I'm going to then plug the next talk after lunch, which is Professor Yuan Ping's talk, which is going to tell you all about, okay, from a first principles perspective, how to actually predict these energies. Yeah. Oh, maybe one more question? No. Yeah, so I would say the major challenge is still kind of deployability. Right now, I mean, we have very good options for measuring some of the same things that quantum sensors are excellent at. So I feel like you have to find specific scenarios where it does make sense. And I do think certain magnetic field sensing and atomic clock is a great example. I don't think there's really a competitive technology that can give you that ability to keep time. And then I do believe that the application of navigation can really benefit from the use of quantum sensor. But it is also right now not cheap, right, to package all these systems and take them outside of the lab. And then once you do that, they don't behave as well as they did in the lab. So, and you know what I was alluding to when talking about NV centers, for example, that you have to do all these things with regards to photonics to basically better extract light. You have to be very careful with surface chemistry to make sure that the emitter remains coherent. And so these are all the things that, well, you need to continue to do to really push the sensor to the almost sensitivity in lab, and then also maintain when you take them out. So I would say that's a kind of the big challenge. Please follow Ilya now.